So we've been slowly building up the tools we need to try and tackle interesting problems. Our aim is not to prove the various techniques that have been described, but to sketch the main features and to point out some very, very interesting consequences which are sometimes hidden. Now we turn to one of the most powerful tools for trying to understand the external phenomena, to understand fundamental results of science, and that is the tool of calculus. In order to establish the basic ideas, we start with a simple example. So we look at a series like that, where this quantity x is less than 1. Even if x was bigger than 1, if I stop after n terms, there is no problem. But if I let n go to infinity, as I will, then it is not permitted, because the terms get bigger and bigger. This thing we know can be summed like this, and we know that x is less than 1, and we have a formula. Now we can write this, we can take a limit as n goes to infinity, Sn of x, you see, and as I said, Sn is a function of n. X is some particular value which is less than 1. But once we look at this x value, and if I change n, the number I get by summing changes. So S is a function of n. So this is function of n. So the limit is an operation on a function. By taking the limit, I start with one function, I end up with a different function. And so that is a special feature. As I said, in arithmetic, the operations are addition, subtraction, multiplication, division, which means that if I take numbers, if I add them, subtract them, multiply them, or divide when allowed, I get another number. So the limit is this very special operation which acts on functions. Since x is less than 1, this becomes 1 minus x. That's the limit. Now we find something very curious. Originally, when I had this held for x less than 1. But I have this formula. If in this formula, if I set x is equal to 2, if I call this S infinity of x, right, then S infinity of x is minus 1. Completely well defined. There is no problem. So this is a puzzle. And this result is only true if all infinity of these terms are kept. If I leave out even one term, this is not true. So for example, let me suppose I leave out x cubed, omit. So I have this series, and this term I throw away. Okay, this is no longer true, but if I add and subtract, then this was left out. I add and put it in, and subtract, that's gone. Then this part is the result which we had, but now I have this term, x cubed. So this time this infinity nu S infinity x cubed left out is equal to 1 upon 1 minus x cubed. A different thing. So you see, leaving out even one term makes a difference. But if I leave a finite number of terms out, they will get suitably modified and the expression will be still valid outside this range. So this thing is a very, 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 very powerful idea. It tells you that functions can have different representations, and the representation is valid in a certain region. If I want to write a representation of this type, then what I can do is I can look at this expression. This thing is true as long as x is not equal to 1. This is true. X can be bigger than 2, bigger than 1, less than 1. This is okay, right? So if x is bigger than 1, then this becomes x right. It doesn't matter that this is bigger than this is fine. But now what I do, right, is I can replace, I can divide by, I look at this and I say that this thing, when I look at it, n going to infinity is a big problem. So there's nothing much I can do. But if I come to this expression here, S infinity, I can I write 1 minus x, 1 minus 1 upon x, right? I multiply, I divide by x, right? Right. So I take the x outside, and I have 1 upon x like this. Okay. So now I can expand this term. So if x is bigger than 1, I can expand. I have 1 upon x into, and I can change the sign with a minus sign, is 1 plus 1 upon x plus 1 upon x. Right. So what you have is, from this point of view, it is difficult because this series has a own character. But once we have got this limit, this 1 upon 1 minus x, then we can have an expansion for it which is valid when x is bigger than 1. So what mathematicians have found is that this process of having region by region different representations is possible, and there are techniques which sometimes go under the name analytic continuation, which tell you how to do this. So it's a powerful idea which is illustrated in this very simple example. So what we have learned from this is that there is this notion of a function, and the function can have representations. The function is up there in abstract space. You can concretely represent it in different ways, and if you have that in mind, then when you got stuck in a certain way, then you can immediately say that maybe I should think about finding a different representation for the function. Now there's a well-known example in the letter written by Ramanujan to Hardy. In the letter, Ramanujan said that 1 plus 2 plus 3 plus infinite number of these is equal to, I think it was like maybe minus 1/6, you see. And this caused Bromwich, who looked at it, saying that divergent series are difficult things, and here he had stumbled on something, and maybe he should read this book, and he suggested some book. But nowadays people know that this result of Ramanujan, actually he had guessed a different representation for this, and this is what he seemed to have done. That if I take 1 upon n to the power of s, and this is called the Riemann zeta function, right? Then if I take s to be equal to -1, right, then I get this 1 plus 2 plus 3. It turns out, and this was a great advance made by Riemann, that S here is a parameter. Before Riemann, Euler had looked at summation 1 upon n to the power of k, zeta of k, and k is an integer bigger than 1. Okay? So the reason for Euler was, as a mathematician, he wanted to solve the problem of this kind. 1 plus 2 plus up to n, people knew how to sum. Then 1 squared plus 2 squared, n squared, there was a formula for it. Then there was a formula for 1 cubed plus 2 cubed plus n cubed. And then there was a formula for 1 to the power of k, n to the power of k. So these are things which mathematicians established. So the question then was, what happens when you do the inverse? What happens if I sum 1k and you sum 1 to capital N? See? And that would be the analog of the formulas derived. And what Euler found, that when k was equal to 2, if you didn't stop at n, if you went up to infinity, this was, I forget the detail, but I think pi squared over 6 or pi squared over 8. So you get a very different type of answer. Instead of getting an integer, you suddenly get a transcendental number like pi, and it comes out of the thing. And this he had discovered. But then along came Riemann, and Riemann had gone and attended some lectures by Dirichlet, and had picked up ideas of complex numbers. So he said, can I generalize this thing of Euler and make it complex, S complex? And once I've done that, then this is a function of a complex variable. And what people were able to prove, that zeta of -1 is -1 by 12, which is the result written down by Ramanujan. So this zeta function was used by Hawking to make sense of a determinant of an infinite matrix. So the zeta function is quite a prominent player in the world of mathematics. It's related to a number theory, and it shows up all over the place. And one of my lectures, I will talk about the zeta function and describe not this, but some beautiful properties of this function, right? Which again are due to Euler. And that kind of result has tremendous beauty in it and tremendous imagination. So coming back to our business of taking a limit of a function, we can immediately talk about the instantaneous change of a function. So let us consider a one-dimensional object, and we have a coordinate x function of t. So we talked about coordinates before. So the coordinates are a way of representing points in an algebraic way. So in one dimension you have one coordinate, in two dimensions you have the x-axis and the y-axis, and you have a point here which has coordinates x and y, and this distance is x, this distance is y, this is r, and this is theta. So this is the kind of picture we talked about. So in this picture, this is a right angled triangle, this is a right angled axis, and just Pythagoras tells you that x squared plus y squared is equal to r squared. So that's Pythagoras' theorem, and what we pointed out was that to understand this triangle and the angle theta, it is convenient to introduce functions of theta So in other words, the same point can be represented as x and y or by r and theta, right? And then Pythagoras tells you that x squared plus y squared is r squared, and that means from here that this implies that cos squared theta is equal to 1. Okay? So this we talked about, and we will be making use of this result later on. For the moment, we just look at one of these. If I wanted to do the two of them, I would say this is a vector, and this is a vector x vector, which is I x plus j y, and this is the unit vector, and this is the unit vector. So the x-axis you describe as a vector here, and y as another vector, and this is a representation of vector. So if I just put a vector on top, it could be 2-dimension, 3-dimension, and for those who like to be extravagant, n-dimension, n maybe 26, just an arbitrary number, or maybe 10. Okay, so those are examples of representing something. But once we've done that, then the rate of change, the derivative, is defined to be x of t plus h minus x of t divided by h, and the limit. So x is a function, and this operation is on a function, and you get a different function, and so dx dt is a different function which you call the derivative, and this rate of change would then be called the velocity. Similarly, if I take dv dt, this is another function, so I can take this, then this would be the acceleration. Right? So immediately you have a notion of velocity which is instantaneous at one instant of time, and you have a notion of acceleration at one instant of time. And this is the cornerstone of mechanics, and this is why Newton invented calculus. He wanted to describe systems in which there was movement, particles were moving, right? And so he had this notion, abstract notion, of a point particle, which is something which has a parameter which you call mass, and it has a position. So the whole subject of mechanics of Newton deals with point masses which have location, right? And so the idea was that there would be some equation, that's the equality sign comes in, the equation on the one side you will have something which depends on the position. On the other side there will be some object which you call the force, which changes, makes the thing change, right? And so this equality turned out to involve the acceleration. So what you have then is the acceleration. This you can write as the second derivative of x, right? So what Newton suggested, and we will just quickly remind you of what it is. He suggested that there is a parameter called the mass, inertial mass, and that mass into acceleration is equal to force. So this is not a definition of force. Force is something which comes from nature. There could be gravitational force, there could be electric forces. So this is something which is an input. So if you know the nature of the force, then that causes a particle on which the force acts to accelerate. And so if you can solve that, by solving I mean given given m so these are vector quantities, but for the moment I ignore the vector because we're talking about concepts. So this is known, given. So by solving you mean given this equation where f is something which depends on x, right? It can depend on x dot as well in general, x, the derivative of x, the velocity, but let's suppose it's like this. Then the problem is find x of t. So that's the problem, that if you're given the law, the solution means you predict the future. You're given some boundary condition and the system is so tight, it will tell you forever and forever exactly where the particle will go. It's an astonishing idea, right? And the whole idea was that there was one particular force which he introduced, and that was a gravitational force. And the gravitational force had the property so the gravitational force you had m, then you had d2x, dt2, and these could be vectors, is equal to g m over r squared. So the particle, there is a central mass here, capital M, there is a little mass in here, and this is the distance, and we are looking at the way this particular particle is moving. We assume that this is a fixed object. We can do some trickery and get around this, but for the moment let's suppose this is a fixed center which is a mass m, and you have a smaller mass m there, and you have this equation. Okay, so if you are on the surface of the earth, this is your little m here, this is capital M, the earth, right? Then we know that m, the acceleration due to gravity is g, that is equal to g m over r earth. Okay, so that tells you that g is equal to g m by earth. Okay, So for the Newton law, you immediately get this result. If I had put vectors here, it does not matter. Then this is telling you the direction in which the particular acceleration points, and you have this particular result. In this case, on the surface of the Earth, the force is acting like this. So if you drop something, it falls. So that's the acceleration, and we know the number. This is 980 centimeters per second per second. So we know what this is. But now we can do one more step. We can write this as g re squared 4 pi over 3 rho of the Earth re cubed, taking the Earth to be a sphere of radius r. So this thing gives you g 4 pi over 3 rho e r Earth. Right. So what you find is that Earth is equal to 3 over 4 pi g over g into so immediately you're learning something. You see, this capital G was measured by Cavendish. It is roughly 6.68 10 to the power minus 8 in my CGS units. You see, when I was young, I had a board in my home. I wrote all the constants of nature in CGS. That's hardwired. So I cannot do anything. I have heard about a thing called MKS, but I have not paid any attention. Okay, in anything I do, I continue to use CGS, right? So what you have is the formula which tells you what is the radius of the Earth in terms of everything which is known except rho of v. So rho of v you can take roughly to be of the order of 1, and if you work this out, you will find you get the radius of the Earth. So this shows the power of estimation. This shows that from very simple starting points, you can get real information which is of interest, right? And if, for example, you put in the real number for this by actually taking a tape and going around the world, the standard way of measuring, of course, and so you measure the distance, you've got this you know, then you find the density. You see? And the density is roughly 5.5 grams per cubic centimeter. So this is the power of this whole enterprise, that it is complicated. Formulas are very important because you want to get the things dead right, because science has progressed. But to get a rough feeling, very often no complicated calculation is necessary. You can get estimates which are very good. So let us look at one more example. This time we will look at the EarthSun system, right? So to do that, what you have is, then we have the m Earth into the acceleration of the Earth around the Sun is equal to g m Sun m Earth over r, right? So the acceleration a for something going around like this is v squared over r. So when something is going around in a circle, then that is the acceleration. So if I put that in, then I get me v squared over r is equal to g m Sun me over r squared, right? So what we find is that this and this cancel, and we get the mass of the sun is v squared r over g. Okay. Let us work this out, because later on we will try and calculate the mass of the sun using very simple physics arguments. So for the moment, let us work this out. How do we work it out? First, we have to know R and we have to know V. So R. Now, this is what I will do. I mean, the one method of working out R is to look at Venus and measure send a radar to Venus and it bounces back, and then look at a particular triangle and work it out, right? Now I will assume that some very clever person has found some way of sending a signal, light speed, and coming back. And we know that roughly 10 minutes. It takes 10 minutes for the light to reach Earth. So it takes, the distance is c into time. C is the velocity of light, right? Centimeters per second, and this is second, so this is length. So the dimensions are okay, right? So what is the t? T is roughly 10 minutes, which is 600 seconds, which I'll write as 10 to the power of 3 seconds. So these squiggles are extremely useful. They reduce the calculation and you get roughly an idea of the number. Okay, so this is, and c I will take roughly 10 to the power of 10 centimeters per second. There's factors of 3 which I ignore. So this immediately tells you that r is roughly 10 to the power of 13 centimeters. Okay. Now we come to, so we have put a tick, we've got that. So now we come to V. V is this is radius r, this is the mass Earth. So what is this? 2 pi r divided by t y. So the Earth goes on the sun 1 year, right? So 1 year, in my list of things I had on my blackboard at many years ago, when I was much younger, and this is roughly pi into 10 to the power of 7 seconds. This is something worth knowing, right? So 1 year is pi. It's actually 3.15, but 3.14 is not too bad. So pi into 10 to the power of seconds is 1 year. Okay, so I have this, I have just found r, so we can immediately work out V is then 2 pi into 10 to the power of 13 divided by pi into 10 to the power of 7. So that is roughly, I ignore the thing, is 10 to the power of 6 centimeters per second. Okay, so we have these. Now G is known. G is like roughly 7, 10 to the power of minus 8, which is roughly 10 to the power of minus 7. So now what is m of s? V squared, V is 6, 10 to the power of 12 multiplied by r, 10 to the power of 13 multiplied by 10 to the power of 7. Why don't I just make it 10 to the power of 8? Because there are factors all over the thing which are ignored. I can justify that for the moment. Let me just say 10 to the power of minus 8. Then what you find is this is 10 to the power of 33 grams. Okay. So again, you see, just from simple rules which are available, we are able to get a mass estimate for the sun. And this kind of technology of estimating things is absolutely the lifeblood of practical experimental physicists. So when I collaborate in the nano lab, everyone else is experimentalists. And so they use this MKS SI system. So what we do is, I work something out using my CGS, and Michael Coe, my collaborator, who is a FRS and National Academy of Science member, but he's a SI person. So he does it in his SI, and then we compare, and they agree. So there is a and I refuse to use his SI, and he refuses to use CGS. So in a way, it's a good check. So what I think is useful is, with anything I do with him, I find that there's always this idea of, is it a measurable thing? If I write an abstract formula, I don't know what the number is. For example, in many books when I was young, I quoted that if water goes around a sink, in the northern hemisphere it goes in one way, southern hemisphere it goes the opposite way, and I believe that. It's only when you put the numbers, you know it's absurd. It is so minuscule that you need an extraordinary sensitive measurement to make. It's when you have hurricanes or tornadoes, huge things, then it makes a difference. But for the thing which is in many, many textbooks, and none of those guys have ever worked out the numbers. They have a formula, and the formula tells you that, and they're happy, right? So for real measurements and for real life situations, the numbers are extremely important, and it's a good habit to have, to quickly put down some numbers and say, does it make sense? Does it work? Right? So that's the kind of situation which we have. So what we have at this stage is a general feeling of using simple arguments. The simple arguments use the laws of physics, maybe not in great detail, but structurally. Structurally, there's a relationship between force and acceleration, and that information is fed in. So you know it's consistent with the laws of physics. And then you make simple approximations, you feed in information that you know without going out anywhere, that Earth goes around the sun and it's 1 year, and you put that bit of information. So now when you look at the phenomena of particles, you see there are simplifications here. The Earth has been treated as a point mass. The sun has been treated as a point mass. So you know there are going to be deviations. And there will be effects which come because these fellows are not point masses, right? But at the first level, this kind of system works extremely well, right? And as the thing moves, when particles move all over the place, what you find is that they're constantly, the velocities are changing, the positions are changing, and everything seems to be in flux, right? But they're governed by these laws. However, it was soon discovered that that is not the case. In all of these changes, the kind of things which are at the fundamental physics level, it turns out that there are certain unchanging quantities. And this was a great discovery. And that unchanging quantity for this example is energy. You see? And so the energy you see, what we had, the energy for a single particle is half mv squared minus v of r, or I'll call it phi of r. So this is the potential energy. And this is the kinetic energy. And so what is phi of r? Phi of r is G ms m. So if I take the derivative of phi of r with respect to r, I get G ms me of r squared, and if I put a minus sign there, I get this. Right. So what you find is, in the case of the gravitational thing, this object has the property that is derivative with respect to r, keeping, there's no t in this thing anyway, so if you do this, you get the force. And when I look at this expression, right, then I can check that if I look at dE dt, right, then this is equal to half m 2v dV dt using calculus minus ddt of phi of r. So this thing, the 2's go away, you have v here, you have m dV dt is equal to minus, and this quantity I write ddt of phi of r, I write as dr dt ddr of phi, right? And so what I find is that this gives you v into G ms I take the v outside. Right? So when I do this, I get this multiplied by v, but this quantity is nothing but the equation of motion, so it is 0. So this is 0. So what you find is there is bookkeeping going on. There is a strict budget, and you have to stick to this budget. There is no messing around. They won't say, well, I'll pay it off next year, or I'll have a deficit of so much. No deficit allowed, nothing, 0 deficit. It has to be exactly balanced. And this exact balance means that there is sharing between two things: the movement part, which is the kinetic, and the non-movement part, which is the potential. So this is a very, very, very powerful example of a conservation law. Later on, people understood that conservation laws are related to symmetries of the system, and that's another story. But it's a beautiful chapter of physics, that things which were discovered in this indirect way by looking at equations of motion and searching for things actually are revealed to be actually fundamental properties which one could have guessed or one could have derived from general principles. So we have now got the basic structure, we have got the concept of energy, and we have got the concept of the velocity, and we have the concept of a position, all of them defined with respect to a coordinate system. So the coordinate picture which we introduced is essential. The coordinate always has an origin, and with respect to that origin, everything is done, right? So in setting something up, we need the coordinate system. And once we've got that, then calculus comes in, and calculus tells us the rate of change of position with time can be made precise using the idea of a limit of acting on a function. So I think we have enough things now to move on to the next stage, which is to see an example where these ideas are used at the atomic level, and where one of the great revolutions of physics took place due to Niels Bohr in 1913. Thank you.